Welcome to The Explainer. Today we are going to tackle two theorems that are seriously the bedrock of calculus, Roll's theorem and Lagrange's mean value theorem. If you're prepping for exams like the JEE or NDA, you absolutely have to know these inside and out. So let's lock them down.
But before we get into the math, let's start with a really simple question. Picture this. You're on a long road trip. You figure out your average speed for the entire trip was exactly 60 miles per hour. So here's the question. Does that guarantee that at some point, even for just a split second, you looked down at the speedometer and it read precisely 60? The answer to that question is really the whole point of the mean value theorems.
All right, let's dive in, starting with the most specific version of this idea, Roll's theorem. You can think of it as the flat case, and trust me, you're about to see exactly why that name makes perfect sense.
Okay, here's the formal definition. But don't think of it as just a rule. It's more like a promise. If your function meets three specific conditions, the theorem guarantees a result. It guarantees that somewhere in between your start and end points, the slope of the curve has to be perfectly flat, a slope of 0. You know, what I love about this is that you can just turn it into a checklist. Condition 1, is the function continuous? Meaning, can you draw it without lifting your pen? No gaps, no jumps. Check. 2, is it differentiable? Are there any sharp corners or weird points? Nope. Check. And 3, this is the special one for Rolls, does the function start and end at the exact same height? If you can check all 3 boxes, you're in business. When you look at it visually, it's just obvious, right? If you draw a nice, smooth roller coaster track that begins and ends at the same altitude, you just have to have a peak or a valley somewhere in the middle. And right at the top of that peak, or the bottom of that valley, the track is perfectly level. The tangent line is horizontal. Slope, 0. Let's make this real with an actual problem, the kind you'd see on an exam. So we've got the function x squared minus 4x plus 3 on the interval from 1 to 3. First, the checklist. It's a polynomial, so yeah, it's continuous and differentiable everywhere. No problem. Now, the endpoints. Let's plug them in. F of 1 is 0, and f of 3 is also 0. Bingo! All conditions are met. So the theorem promises there's a point C. To find it, we take the derivative, which is 2x minus 4, set it equal to 0, and we get C equals 2. And since 2 is right there between 1 and 3, the theorem works perfectly.
Okay, so now that we've got Rolls down, let's zoom out and look at the bigger picture. This is Lagrange's mean value theorem, or just MVT for short. It's the more powerful, more general version of the same idea. Now, look closely. This feels familiar, right? We still need continuity, we still need differentiation, but notice what's missing? We've dropped that third rule about f of a having to equal f of b. And because of that, the conclusion is different too. It's not just about a flat tangent anymore. Now it says the tangent at some point C has a slope equal to the average slope over the whole interval. And boom, we are right back to our road trip. This is the math that proves our hunch was right. The MVT is the guarantee. It promises that at some point C during your drive, your instantaneous speed, the number on your speedometer right at that moment had to be exactly the same as your average speed for the entire trip. The instantaneous has to meet the average. So let's run through a quick example. Here's a function on the interval from 0 to 1. Again, it's a polynomial, so continuous and differentiable. Check and check. Next, we find the average slope with that formula on the screen, and we get 3. Okay, so now we find the derivative, which is 2x plus 2. The theorem says that the derivative has to equal our average slope of 3 at some point. We solve that simple equation, and we find that c equals 0.5. And since 0.5 is right in our interval, the theorem holds true. All right, now for my favorite part. This is where we connect the dots between Rolls and Lagrange's. This is the aha moment where it all really clicks. This slide lays it out so clearly. Rolls is the specialist, right? It's got 3 strict conditions and gives you a very specific result, a perfectly horizontal tangent. Lagrange's MVT is the generalist. It's more flexible, has fewer conditions, and its conclusion is broader. There's a tangent line that's parallel to the line connecting the start and end points. And here it is, the big reveal. Roll's theorem isn't a different theorem at all. It's just a special case of Lagrange. Seriously, think about it. Look at the MVT formula. What happens if you add in that third condition from Rolls, the one that says f of a equals f of b? Well, the top of that fraction, f of b minus f of a, just becomes 0.
And 0 divided by anything is 0. So Lagrange's formula turns into f prime of c equals 0, which is exactly Roll's theorem.
So what does this all mean when you're staring down an exam paper? Knowing the theory is half the battle. Knowing the common traps, that's the other half. So let's get into some pro tips. These are the classic mistakes that students make again and again. The biggest one by far, just jumping into the derivative without checking the conditions first. Another easy trap is mixing up the intervals. Remember, it's a closed interval for continuity, but an open one for differentiability. And a big one, assuming c has to be a single unique number. Keep an eye out for these. They can save you some easy marks.
Now, examiners love to throw curveballs with functions that have hidden problems. So you have got to be on high alert for things like the absolute value function with its sharp point at 0, or cube root functions, which can go vertical. These are designed to be trick questions to see if you're actually checking the differentiability condition or just going through the motions.
This is such a subtle but absolutely vital point, especially for multiple choice questions. Think of a wavy function like a sine curve. Inside a big interval, it could have lots of peaks and valleys where the tangent is horizontal. The theorems only promise you'll find at least one point C. They never, ever say you'll find only one.
And let's end with this thought. The mean value theorem shows us this deep, beautiful connection between the big picture average and a single in-the-moment value. This isn't just some abstract rule in a math book. Where else do you see this principle? In economics, in physics, maybe even in your own life, where the average over a long time is guaranteed to be perfectly matched by a single instant. It's a pattern that, once you see it, you start to find everywhere.